So over here we have a completely different situation, because now the current will actually move from here, remember, from positive to negative, will flow over here, and will actually now split itself, since this is a parallel connection, will split itself into this side and this side. So the current here, we'll call it I1, will split itself into two different currents, I2 and I3. And now this current, you notice that since the split itself, means that when you add I2 and I3, it should give you back I1. This is Kirchoff's junction rule, because it's a junction here and it's another junction here. Kirchoff's junction rule, or Kirchoff's current rule, states that when a current goes through a junction and divides itself, the sum of the dividend currents should give back the initial current. So this I1, I2, I3, I2 pass through this 10 ohm resistor. And now since this is a actual connection due to this 40 ohm resistor which has been added between A and B, the current will actually flow over here. So current I2 will flow here and will be going back over here. Current I3 will flow over this 50 ohm, will be going back here, and we get back our current I1 which go here. So now what we need to calculate the voltage here. So we know that voltage is equals to current times resistance. We know the resistance here is 40 ohm. We need to get the current here, and the current here is I2. So we need I2. So what we're going to do, we'll need Kirchoff's laws. We'll have to do the loop law, the Kirchoff's current law and Kirchoff's loop law. So we'll call this, we'll make two loops going in the same direction. This is loop 1 and this is loop 2. So loop 1, which means that current will be going like this. I mean the loop is going like this. Will fall down here and will fall down here. So going this way in the clockwise direction. Same goes here. Current, the loop is going like this, goes down and then climbs up. Okay, let's now go according. So we'll applying Kirchoff. I'm writing socks. Applying Kirchoff's. Is that right, Kirchoff? I'm writing socks. Applying Kirchoff's current law or current rule, whatever. It states that I1 is equals to I2 plus I3. So we'll baptize this as equation 1. I will go further to do other things. Equation 1 will just wait for us. So next thing is applying Kirchoff's voltage law at loop 1 or L1, whatever, at loop 1 or subscript 1 or whatever. So Kirchoff's voltage law states that the algebraic sum of all voltages in a circuit or in a particular section of a circuit will sum up to 0. I repeat after it, the algebraic sum of all the voltages in a particular loop in a particular section of a circuit should give you 0. So talking about algebraic sum at loop 1, what do we do in loop 1? There are rules to follow. The second rule to follow, or the rule to follow for this law, is that when the loop goes in the same direction, this L goes in the same direction as a battery or voltage, basically like this one, then we take the value to be positive. And when they're going in different directions, loop voltage, we take negative. As for the current passing through a conductor, we're taking a current passing through a conductor because of this law. The current times the resistor. Did I say conductor? Sorry, resistor. The current passing through a resistor will give us a voltage. So these two components, that is the current passing through here, gives us a voltage. So when the current passing through a conductor has the same direction as the loop, we instead take negative. That's counterintuitive to the voltage itself. And when the current and the loop are in different direction, then yes, if you guess it right, it will be positive. So we'll take from here. The loop goes up and so is the current. By convention, current moves from the positive terminal to the negative terminal. So the voltage pointing this way, loop pointing this way. Therefore, this is 12 volts. The next component in loop 1, the loop is going downward and the current passing through this resistor is going downward, the same direction, which means it will be negative. So this will be negative 30 I1. And finally, the current I3 passes through the 50 ohm in this direction, the same direction, is passing in the south direction, and so is the loop going downward, that's south. So same direction, negative, negative 50 I3. So the algebraic sum is equals to 0. So this is negative, positive. If I bring this 2 the other way, we'll get 12. We don't need to put the volt here, just ignore it. That's the units. All of them are in volts, by the way. This current, remember, current times resistance equals to voltage, so all of them are in volts. So this will be equals to 30 I1 plus 50 I3. So since this is an equation, this is an equals to sign, this means that 30 I1 plus 50 I3 is equals to 12. This is our equation 2. Equation 2, just sit tight with us. So now we'll go to applying Kirchoff's voltage law at loop 2. Okay, subscript 2, whatever you call it. So we'll do the same thing over here, loop 2. We'll start from the 50 ohm. The loop is going in this direction, but the current is going downwards. So different directions, positive. So that'll be 50 I3. The next component, the loop is going in the east direction, and so is the current passing through the 10 ohm resistor, going through the same direction. Therefore, this will be a negative I2. And finally, the loop goes downward, L2 goes downward, and so is the current I2 passing through the 40 ohm resistor. So this will be a minus 40 I2 again, and the algebraic sum is 0. So we get a 50 I3. 10 minus 40, since they're having the same I2, we could factor our I2 and we are left with 10 minus 40, which gives us 50 I2 is equals to 0. Now we can bring this 50 this other way. We can bring the 50 I2 the other way, so that we get a 50 I3 is equals to 50 I2. Both of them have 50, and we discovered that I3 will be the same as I2, which is incredible. Actually incredible. So now that we know that I3 is equals to I2, we can equate I2 I3 in equation 1, and we will use equation 1 to equate here in equation 2. So since we are looking for I2, but we know that I2 is equals to I3, let's just use I2 and equate it. Let's use I2 is equals to I3 and equate it here, so that we'll get only I3, and with I3 only we'll equate it in equation 2 to get a full equation of only I3s. So for I3, I answer of I3 is I2. So number space we have to turn the page. So substituting, substituting I2 in equation 1. Remember, equation 1 was equals to I2 plus I3. When we substitute, I1 will be equals to I3 plus I3, and we'll get our I1 to be equals to 2I3. So so this is now equation 4, and hence we can now substituting equation 4 in 2. Equation 4 was 30I1, equation 2, sorry, was 30I1 plus 50I3 equals to 12. So we have I1 is 2I3, so it is 30 in bracket 2 I3 plus 50 I3 is equals to 12. And there's it. We have a full equation of I3. Solve for I3 and then we get I2, which is the equation itself. So 30 ups. 30 times 2 will give us 60 I3 plus 50 I3, which equals to 12. So this gives us 110 I3 is equals to 12, and hence I3 is equals to 12 followed 110, or simply I3 is equals to 0.1111. Okay, to this map is 0.11 amperes. And now remember that I2 is equals to I3, so this implies that I2 is equals to 0.11. Perfect. And now we can go back to the equation where we look for the voltage at AB now. We know that voltage equals to current as ampere, so it is current times resistance, so it is I2 times the resistance there, which is 40. So I2 is 0.11 times 40, and this, if you bank it on calculators, will give you 4.36 volts. Perfect. So now let's go to Roman 2. So finally, Roman 2 states that the current flowing through the 40 ohm resistor. So we have to calculate current flowing through the 40 ohm resistor, but we've already done that. So I2 will simply be, well, I2 will be equals to the current flowing through the 40 ohm resistor, and therefore the current flowing through the 40 ohm resistor, oops, I have to put ohms, is equals to 0.11 ampere. So that's basically it for the B part, for the A and B parts. Thank you for watching. Don't forget to like, subscribe, whatever else. See you in the next question.